Hello to the video, Vectors in 3-Dimensional Space Part 1. In this video, we take care of the basics of vectors in 3-dimensional space. Here we describe the vector A, which is drawn in purple. Vectors can be specified in the coordinate notation. In 3-dimensional space, 3 vector components are required to describe a vector. These vector components are identified either with the indices 1, 2, 3 or with x, y, z and written down in columns. The vector component with the index x describes the position of the vector in 3-dimensional space in the direction of the x-axis. In this example, the value 5 was chosen for the x component. The x component is plotted in the Cartesian coordinate system in the direction of the x-axis. The vector component with the indication y describes the position of the vector in 3-dimensional space in the direction of the y-axis. In this example, the value 4 was chosen for the y component. The y component is plotted in the Cartesian coordinate system in the direction of the y-axis. The vector component with the indication z describes the position of the vector in 3-dimensional space in the direction of the z-axis. In this example, the value 7 was chosen for the z component. The z component is plotted in the Cartesian coordinate system in the direction of the z-axis. The starting point of the x component and the ending point of the z component describe the vector, A, in the Cartesian coordinate system. The length of the vector called the amount can be calculated by applying the Pythagorean theorem twice. For this we draw an auxiliary vector, A', which is defined by the vector components x and y. Since the y vector component is at right angles to the x vector component, the vector components together with the vector, A', form a triangle at right angles. With the help of the Pythagorean theorem we can calculate the amount of the vector, A'. Already converted here to calculate the amount, A'. The z vector component is now perpendicular to the vector, A'. With the z vector component and the amount, A', the amount of the vector, A, is calculated using the Pythagorean theorem. Now you can use the formula for the amount, A', instead of the amount, A'. Finally, the root that is squared is shortened and you get the final formula for the amount of the vector, A. The vector, A, can also be described by means of the amount and the direction angles alpha, beta and gamma. The angle alpha of the vector, A, is between the x-axis and the vector, A. The angle alpha of the vector, A, can be calculated using the cosine function. This results from the fact that the x-vector component forms a right-angled triangle with the vector, A. The angle beta of the vector, A, is between the y-axis and the vector, A. The angle beta of the vector, A, can be calculated using the cosine function. This results from the fact that the y-vector component forms a right-angled triangle with the vector, A. The angle gamma of the vector, A, is between the z-axis and the vector, A. The angle gamma of the vector, A, can be calculated using the cosine function. This is because the z-vector component forms a right triangle with the vector, A. The vector components can be expressed by means of the alpha, beta and gamma angles and the magnitude of the vector. A vector can be described in the spherical coordinate system, which is also called spatial polar coordinate system, by means of two angles and the amount. The azimuth angle phi is the angle between the x-axis and the perpendicular on the x surface and y surface to the vector, A. In other words, the azimuth angle phi is the angle between the reference direction and the orthogonal projection of the vector, A. The polar angle or pole distance angle theta is the angle between the pole direction, which here is the z-axis, and the vector, A.